So welcome to another FEA laboratory video, and so we have finished this plate and the last one for now. Okay, we'll be doing much more, but for our experiments is the column analysis. Okay, so we can do a buckling analysis on this particular column. So they have given a few characteristics here about the breadth, depth of the column, how much force, the force being applied is not mentioned. P is the force. We need to find at what force will the column buckle. Okay, this P, we need to maybe calculate that. So yeah, the length is given. This is a rectangle. Okay, I drew it as a cube, but it's actually a rectangle surface because 210 and 280. And then it's an aluminum. Okay, see, this is the big difference here. It's aluminum now, and it has 70 gigapascal as its Young's modulus. Okay, so let's head on over to our static structural now. Let me bring that in. Now this much time we have been doing with structural steel, so it was easier. Ippo pathina we have, oh sorry, very sorry, I unknowingly clicked. Okay, the name changed because of that. It's okay, fine, let it be. So let me just change it back. Structural steel. Okay, we don't need this anyway, but so here we are starting with aluminum now. Okay, so for aluminum we need to enter the Young's modulus which is given. So here just click on here, you will be able to create a new material. We'll call it aluminium. Okay, and then now this aluminum needs all these properties, right? But structural steel click panna, you got a lot of properties, right? So similarly for aluminum, all these properties are here. So for Young's modulus abdin pathina, it's a part of the where is it? Yeah, I believe it's part of the isotropic elasticity. Okay. Okay, so we have the Young's modulus and Poisson's ratio. So Young's modulus is in megapascal. It's going to be 70,000, right? So it's 70 gigapascal that was given. So 70, and then Poisson's ratio is 0.3. We need to know that, or it's quite simple. And also they had given the okay, I didn't mention here, they had actually given the compound the yield stress, right, which we did last time also. They had given that here. I forgot to mention it here. Okay, so under strength you have the compressive yield strength that is given. Actually, I forgot to mention it in the PPT. So that is given for you as 240 megapascals. Okay, so that also we will take in. Okay, so we have the Young's modulus, Poisson's ratio, and this value. So our aluminum is ready now. So we can go back to here, go to geometry, and we need to draw that particular rectangle that we had. Oh, again I clicked its opening space claim. Just wait a second. Okay, let's open design modeler because that is what we want. And if you are familiar with space claim, please use that. It is very much easier to draw in that. Okay, I'm making this so it will be helpful for people who are using a different version, a lower version of Ansys. Okay, so again we can do the same grid options here. Snap to grid and units millimeter, don't forget that. So if you remember, our diagram is go to the PPT, it's like 210 by 280 mm. So it's up to you how much you want to keep this as. So for our case, let's just keep it somewhere around 100 if we need. Okay, and we'll keep this at 1. Look at that. Okay, and then we'll go to draw, and then we'll draw the rectangle. So I'm not sure what will be the length. So I'll just draw a rectangle, go to dimensions. Let's take a look at how they pan out. So it's 200 and vertical is 400. Okay, so what do we need? We need the vertical to be 280. Okay, so this is supposed to be 280 and the other one is 210. Okay, so this is supposed to be 210. So it is not exactly in the center. So if you do want your object to be exactly in the center, you can, like I showed you the last time, you can do this as well. So from here to here, you can have something like 280 by 2, which is not 80. It did not come properly. So we'll just I believe it's 140, right? 280 divided by 2 is 140. So that went to the center. And this side also similarly take horizontal from here to here. I think it will be just 5 mm difference or something. Okay, so 210 divided by 2 will be what? 25, right? 150 should be, yeah. Sorry, it should be 155, correct? Then only you will get 155 plus 155. You should get 210. Okay. Yeah, I got my maths wrong. It's supposed to be 105. Okay. Yeah. So this is what we are looking for. So yeah, basically we just need to ensure that this is 210 and this is 280. That's more than enough for us. We don't actually need it to be in the center. It's just for our analysis purposes. Okay, so this is not a big requirement. So yeah, we have our rectangular base of the column now. So we need to next, we can extrude it. So extrude the sketch for it's supposed to be length was 2.2 meters, right? So 2200. Hit generate. So we will get our column now. So yeah, it does look like a beam because we drew it in this direction. You can draw it in the other axis as well if you want, but this is just simpler to do. I just took it in this way. Okay, it's up to you. You can do it in any other way that you want. No issues. Okay, so we just going to okay, it's something like this. Fine. Now it looks like a column. So we need to apply a force. Like we are trying to find what is the force that is going to be applied here for the system to buckle. Okay, so let's close this and open up our mechanical. So as usual, please wait. Now the point P, right, where we need to find that is a question given for us. Okay, what is this load? Sorry. Now the model has come. Okay, so what is this load P? Okay, this under axial compressive load P, which will make my what is the critical load which is going to make this column to buckle. I hope you remember buckling, right? You would have learned some analysis of this. So if you have a force here and this is fixed here, this will have a buckling like this. You would have learned about this formula and all. Crippling load or buckling, you would have learned about that, right? So that is what we are trying to do here. Okay, so yeah, so what we will do is first we'll mesh it. I'll just go generate mesh. This seems fine for now. Okay, like this is not a good mesh. You have to mesh it much more further, but for our purposes this is much more than enough. Okay, so first thing what we need to do is yes, you need a force, but before that we'll just give a fixed support. Okay, so let's assume that this is our top face. So bottom face we will fix it. Okay, and then you will have a force on the top face. It has to be in the negative z direction, right? So we'll go with components, and in the z axis we'll give it as see, since we don't know what is the force only, we are trying to calculate it, right? So we'll give it as -1. Okay, so maybe I'll keep it here. Okay, so yeah, so we have column and the force is being applied here. Okay, and in solution we'll, as usual, we'll just take a total and we'll take our equivalent also just for analysis. Okay, then you hit solve, and yes, it did solve for what is the deformation and what is my equivalent stress it did. Okay, so you can't see much change here because we gave the force as 1 Newton. Okay, it's not going to do much a big difference. You can try it out. You can just maybe change this negative 1 Newton into negative, let's say 100 Newton, and you can just see how your answers change. Okay, see, you can see how the values have differed now. Okay, there is not much change to the diagram, or maybe we can't see it clearly, but these values have changed now. Okay, the deformation and the stresses. Okay, so what we are trying to find here is basically how much it is going to buckle, or how it is going to buckle. So again, we will just keep it at 1 Newton. Okay, so to solve this buckling, you would have learned some formulas, I believe. P crippling, you would have written some formulas and you would have solved it. In FEA, there is a way you can do it. So let me just come out of here. Okay, so there is something here called eigenvalue buckling. Okay, so you can bring that here. Okay, and I can take the solution from here and then put it into this model. I can transfer that here. Okay, see what I did? I passed on the solution from here to there. Okay, now what I can do is I can open up this particular what eigenvalue buckling module that I opened. It's again in Ansys mechanical only. It's no other new module or anything. Okay, so we have now we have a new thing here, right? Eigenvalue buckling is here. Okay. Okay, so before we do that eigenvalue thing here, we actually forgot something, right? We had actually assigned 2 materials for the model, if you remember. Okay, so what we have to do is we have to change this to aluminum, which I did not do in the first place. Okay, so come back to our original mechanical and we need to change this, and then we need to solve. Okay, so I forgot that it was actually solving it in static structural. Okay, aluminum, I think we missed some data here. Okay, yeah, I unknowingly had suppressed that. Okay, fine, no issues. So we'll come back to our model here. Okay, we need to update this, so let's exit this. We will go to our model again. See, just because I missed material assigning, the whole system did not work. Okay, so it was the material was assigned to structural steel. It's always like that. The general material is always structural steel, so we need to change it to aluminum, which I did not do. So for that, it's very simple. Just click on the solid, okay, and assignment, and click on aluminum. That's all. Okay, so it will change to aluminum now. And yeah, other process is the same. Support, force, and what we already did, all that is correct. There is no change in that. And yes, it did. See, now the values also changed because it's a different material now. Okay, so okay, so let's go and try that eigenvalue thing where it's working now. Okay, so one way is bringing it here. Another way to do it is from the solution you can transfer data to new eigenvalue buckling. You can do this as well, so it will just go directly here. Okay, so setup, again it will open mechanical for you. Takes patience to do here. Okay, So we are here. Yes. So now we can see we have the pre-stress already. Pre-stress in the sense the analysis that we have done with the 1 Newton value, right? That should come into here. That is the aim. That did not work the last time because we assigned, we assigned the material wrongly and we did not, solve it properly. There was an issue there. Okay. Now we have no issues here. So we have the value from the previous thing. So we don't have anything much to do. So we just need to hit solve. Okay, so it had completed the solution. Now, like the last time, let me see if I can get my model to stand up. Okay, we got it to stand up in a sort of way. Yeah, so this is our deformation and equivalent stress. Okay, and total equivalent we got, and if you, this is for that one, okay, that does not change, it is still the same. And if you take a look at your solution, click on this solution here, you can see you have some values here, right? So 1 and 2. So this number 1, this value, right, this particular value which is here, you can copy it, you can export it as an Excel also. So this particular value which is here, 7.7 into 10 power 6, so that's like 7.7 megapascals. Okay, so that will be the critical load that you can, or the force that you can apply for this particular column to buckle. Okay, so you can even check that out if you want. You can go apply that force, and okay, you shouldn't have eigenvalue that time, you'll have to change that as well. So if you go do that, you can also see how it deforms, all those things you can check. Okay, so typically you can you can do a comparative study with the column buckling that you have learned in your structures module. Okay, so adula irukra same principle is in that there will be different, right? If both sides are fixed, one end fixed, one end is free, all those things will be there. You can try those simple things here. Okay, so with that, your how many experiments you have completed? We have done first 3 experiments of your analysis side, and in the next video or in the next class we will be taking a look at the tapered wing and the composite laminate structure. Okay, further we will take a look at the coding in later classes. So thank you.